Okay, I think we can go ahead and get started for the M cubed seminar. And I'm happy to, is this a little echoey?
It is.
Okay, maybe I'm too close to it. Let me try that. Better? Okay. I don't know how to use microphones, I guess. So I'm pleased to present Milena Corcos. Milena got her PhD from Sorbonne University in Paris in instrumentation, remote sensing, and observations for the ocean, atmosphere, and climate sciences. Her PhD focused on the effects of gravity waves on tropical cirrus cloud life cycle using superpressure balloon observations. She graduated in 2023 and came to Boulder last summer for a postdoc at Northwest Research Associates, right across the street over there, to work with Joan Alexander on gravity waves. And Milena just said a few days ago she got hired as a research scientist, so congratulations.
Probably better than I'm
All right, so hello everyone. Can you hear me well? All good? So I'm going to talk about the observation of gravity waves in the tropical Tropopause layer using superpressure balloons from the Stratiol 2 campaigns. And I want to take a moment here to acknowledge the contribution of all my co-authors that are listed below here on this slide. So for a little bit of context, in the tropics, deep convection excites a broad spectrum of waves, from planetary scale waves at the lower frequency end to the gravity waves that can have periods as short as a few minutes and horizontal scales as low as that of single convective cells. But despite their small scales, gravity waves impact the whole atmosphere, from influencing synoptic systems to being, with the planetary scale waves, an essential driver of the Quasi-Biennial Oscillation, or QBO, that is represented on my slide here. So the QBO is an oscillation of the zonal mean, zonal wind. It is a major feature of the tropical stratospheric circulation, and it impacts the climate from modulating the MJO to impacting the precipitations in the tropics and the northern hemisphere surface climate. For now, the general circulation models are too coarse to fully resolve the gravity waves, and they're included using parameterizations that represent their main contribution in shaping the mean flow. The representation of the QBO in these models is particularly challenging. For example, not all models do have a QBO, and the ones that do exhibit an amplitude that is too low in the lowermost stratosphere, as we can see on this figure, with a comparison to the NWRA interim dataset. Since the beginning of its recording, the QBO has showed some sort of regularity with its oscillation, but very recently we started to observe some disruptions of the QBO, as we can see here in 2016 or in 2019. And the evolution of the QBO in a changing climate is unclear. For example, there isn't a consensus on how climate change will affect the QBO period. So this is calling for more observational constraints in order to improve our parameterizations and enhance our representation of the QBO in our models. Recent studies have showed that the main uncertainty in representing a realistic QBO in the models is linked to the parameterized gravity wave drag. For example, in Wacom, the convective gravity wave parameterization that is implemented is missing the highest momentum fluxes, as you can see here, on this figure that compares the momentum fluxes distributions between Wacom and observations from the balloons in the tropics. The figure on the right presents gravity wave spectra in terms of momentum fluxes and phase speed, the same for Wacom and the balloon observations called pre-Concordia-Z. So the heating depth is setting the spectra of waves that are represented here. And the specificity of this Wacom 6 is that the parameterized gravity waves take information from the represented convection in the model, but this heating depth has been artificially lowered in order to enhance the presence of the lower phase speeds here, and that resulted in a better representation of the QBO. Reversely, if we take the same scheme, but this time we are using observations in order to have information about this heating depth, we have a completely different spectrum that is represented by the blue line here. So this time, we have a better representation of the higher phase speed waves, but we can see that the lower phase speed ones are missing when they have high amplitudes and seem to be key for the representation of the QBO. So we can wonder where these waves are from and why they are not represented here. An hypothesis on that matter is to say that this parameterization only represents the waves that are generated by the higher frequency variability of the convection. It is called the non-stationary component of the convective gravity waves. And while this component is, of course, essential for the drive of the QBO, some studies have showed that the stationary component actually gathers waves that have higher amplitude and lower phase speeds, and so it might fill in that missing gap in the spectrum that we saw earlier. This stationary component is triggered by the interaction between the background wind and the convective heating that is seen as more steady, and that will act like a barrier to the background flow and will generate waves almost topography-like. For example, Alexander et al. In 2006 showed the presence of these waves when there is wind shear at the top of the cloud. So this mechanism is called the moving mountain mechanism, as the clouds are moving, and it is currently asking for more observational constraints as it's being implemented in Wacom in a parameterization. So balloons have been historically a tool for in-situ observations in the atmosphere. And Strateol 2 is a French-American project that builds on a long history of ballooning. It covers 50 different flights that will be launched during 3 different campaigns in order to enhance our knowledge of the atmospheric processes in the TTL, and especially the troposphere-stratosphere interactions. The specificity of these balloons is that they are called superpressured. It means that once they reach their equilibrium level, they will follow the airflow for several months, drifting with it. And so we will have instruments flying, drifting with the flow, and having observations on the dynamics, the transport, and the microphysics. And especially, all the balloons were carrying an instrument called the T-SEN that was recording the pressure and the temperature at a 30-second time resolution, which allows us to resolve the whole spectrum of the atmospheric waves. For now, 2 campaigns already took place in boreal winter 2019 and 2021. You can see on this slide the 2 maps corresponding to the 2 campaigns with the trajectories of the balloons. So the balloons were launched from Mahé in the Seychelles, and as you can see, they flew in the whole tropical band at 2 different equilibrium altitudes of 20 kilometers for the STR flights and 18 kilometers for the TTL flights. If we look at observations from these balloons, so direct raw observations from one of the flights, I'm showing here a time series of the horizontal wind here that is inferred from the successive positions of the balloons, as we just said that they are drifting with the flow. And then below the corresponding observation of pressure and of temperature. So we can see that there is a bunch of signals that are impacting these observations. It is well described by the power spectra on the right part of my slide, we find the planetary scale waves. But as we can see, we observe the whole spectrum of gravity waves with periods as short as a few minutes. Another interesting feature of this spectra is this bump that we see around the buoyancy frequency that corresponds to the balloon's neutral oscillations around their equilibrium level. So this can be easily filtered out, and so we can understand clearly that the balloons are giving observations in the whole tropical band in an intrinsic frame as they are drifting with the flow, and they're able to resolve the whole spectrum of waves. So I'm going to show in this presentation how to use these observations in order to study the gravity waves activity in the tropics. And particularly, I will answer to 3 different questions. The first one is to see how the observed gravity wave mountain fluxes vary with their convective environment, as we know that convection is the main source of gravity waves in the tropics. The second one is focusing more on these moving mountain waves that we mentioned in the introduction. And that is interesting here as the parameterization of this mechanism is currently being implemented in Wacom. And finally, what is the contribution of these waves to driving the QBO? And these 3 questions are assessed in 2 papers, one that I published during my PhD, and one that is still under review that we wrote during my postdoc. So we will start by looking at the relationship between the observed gravity waves and the convection in the tropics. So first, to study the gravity wave activity from the balloon observations, we need to calculate their mountain fluxes. The mountain fluxes are inferred from the horizontal wind disturbance and the vertical velocity disturbance. The first one, as we said, is just from the successive positions of the balloons. But the second one, the vertical velocity, is not exactly a direct observation. Indeed, once the balloons reach their equilibrium level, their volume stays constant. So they will follow isopycnic surfaces when the air parcels are following isentropic surfaces. And the difference between the two is represented on my schematic here. So what we do is that we use the pressure observations that are linked to the balloon vertical motion, and we transform it from isopycnic to isentropic with the second line of calculation on my slide here. The last step is to get the perturbations, and we use a wavelet analysis for that. So the wavelet analysis allows us to decompose the time series in the period time space, and we select 2 ranges of periods of interest. We are calling the whole frequency range with periods up to a day, and it will be represented in blue in my following slides, and the higher frequency range with an upper bound of an hour, and it will be represented in red in my following slides. We can see here that the lower bound for these 2 ranges is 15 minutes, and which shows that in order to not be impacted by the balloon's neutral oscillations that I mentioned earlier. Now that we have information about the gravity wave activity, we need to have information about the convective environment of these observations. So we are using maps of brightness temperature from geostationary satellites, and we are locating the nearest convective spot from the balloon as the nearest pixel with a brightness temperature below 235 kelvins. And we measure the distance between the two, and this distance will be our convection matrix. So we are looking at how far are we from convection. The result is showed on this GIF here, with the balloon as a white circle, the nearest convective spot as a green circle, and the distance between the two as a straight line. So before I move on, just as a recap, now we have at 1 hour resolution, because that's the time resolution at which we treat these geostationary satellite images. So we have momentum fluxes for the two different ranges of frequencies and the corresponding distance to the nearest convective cell. Before I move on to statistical results, I just wanted to talk about a study case that highlights well the direct link between the momentum fluxes that we observe and the convection around the balloon. So I'm talking about a convective event that happened the 15th of January 2020. One balloon was flying over this big convective cluster that was moving eastward for around a week. If we look into more details at what is happening during that event, I'm showing on the left part of my slide maps of brightness temperature between the 14th of January evening in the upper left panel and the 15th of January evening in the lower right panel. You can see on all of these maps the balloon as a white circle. So you can see that it stayed above this convective system the whole time. And then on the right part of the slide, I'm showing the corresponding observed momentum fluxes. And I've circled in yellow the two maps that correspond to the peak of momentum fluxes that is observed. So it is interesting here to see that this peak occurs before the spreading of the very cold blue kernels. It is happening during the development of the convection. And so we can see here in situ that the generation of gravity wave happens during this development, and this was already showed in different models, but it was interesting to see it in situ. So now we can move on to more statistical results that link the gravity wave activity and the convection. At a synoptic scale, on the left, I'm showing how momentum fluxes evolve with distance to convection for the whole frequency range in the upper panel, the higher frequency range in the middle panel, and the corresponding number of observations in the lower panel. So the striking feature of this figure is the monotonic decrease of momentum fluxes when we are getting further from convection. And this decrease is even steeper for higher frequency waves. And we can explain that with the little drawing at the bottom of the slide that shows that higher frequency waves will propagate more vertically and they will be harder to observe further from their source. The second thing I wanted to say about this figure is that close to convection, we can see that momentum fluxes can vary a lot. The box plots are quite wide. So this is highlighting the intermittent character of the gravity waves, and it can, for example, be explained by what we just saw earlier in the study case. And finally, when we are getting far from convection, we can see the opposite behavior with the values of momentum fluxes that tend to a background value of around 3 millipascals for the whole frequency range. The last thing is that we saw convection everywhere, as more than half of our data was seen less than 200 kilometers away from a convective cell. Then we can move on to the planetary scale. So here I'm showing boxes of average momentum fluxes, so boxes of longitude, for the whole frequencies range in the upper panel and higher frequency range in the lower panel. So what we can see here is a resemblance between these two maps, with the higher momentum fluxes above the continents and above the maritime continent. And so we can clearly see a relationship between the momentum fluxes, so the gravity wave activity, and the convection activity. We have higher momentum fluxes where convection is more active and less in a more quiet region. So now we've described the observed relation between the gravity wave activity and the convection, and we can focus on this specific component of the gravity waves that are called the moving mountain waves. And we're going to see what part of our observed momentum fluxes can be attributed to these specific waves. So to refresh a bit our memory about the generation of these waves, I'm showing here a very simplified schematic of it. So in the presence of background wind, the convective heating will act like a barrier and it will generate waves almost topography-like. And these waves will propagate opposite to the wind. But the cloud is moving. We make the assumption that it is following the steering level wind, so the wind at 700 hectopascal, and the waves that are generated will have a phase speed that is close to the speed of the cloud, and this time they will propagate opposite to the wind that is relative to the motion of the cloud. So, to select these waves in our dataset, we're going to need 3 different information. The wind at 700 hectopascal, that represents how the convection is moving around the observations, the phase speed of the waves that we observe, and the wind that is relative to the motion of the cloud. So I'm going to start to explain by explaining which variables we can get from the balloons. I've already explained earlier how we can get the mountain fluxes, and the calculation of the phase speed of the wave is also inferred from the balloon observations. It is following the same methodology that is described in Vincent et al. 2014. But this time, we cannot only select ranges of periods of interest, because we need to select the wave packets that correspond to these moving mountain waves. So we are using an S transform, and at each time step, we get each one of the wave packets that are present. We calculate their corresponding mountain flux and phase speed. But as this creates a huge data set, we decided to only retain the 2 main wave packets in terms of amplitude, as we know that these moving mountain waves should have a higher amplitude. And also by doing that, we're already retaining 40% of our observed mountain flux. The last step was to calculate the ground-based phase speed of the waves. The balloons are following the airflow. They are giving intrinsic information, but the motion of the cloud is in the ground-based frame, and we need the phase speed in the ground-based frame as well. So we're adding a term to project the wave direction of propagation into the background flow to our intrinsic phase speed. So now we have everything we need in terms of information about the gravity waves, and we can get information about the convection. So we used IMERG dataset in order to retrieve the convection around the balloons. We decided to define the convective points as the pixels with a precipitation rate higher than 5 millimeters per hour. We only retain the ones that are in the vicinity of the balloons. So here we define it as in a radius of 300 kilometers. And we get, for each one of these points, this steering level wind, so this 700 hectopascal wind that represents the cloud motion, and we get it from ERA 5. So on my picture here, I've put as a background a map of brightness temperature, just for context. The little blue crosses is where we find our convection points. The ones that are in the vicinity of the balloons are in light blue, and their steering level wind is represented with a black arrow. So it's reassuring to see that in one cloud, all the little arrows are going in the same direction. So, as a recap, we have now wave properties from the balloons. At each time step, we have 2 wave packets, and we have their corresponding ground-based phase speed and mountain flux. And we have information about the convection, so this average U700 hectopascal around the observation. And we can move on to selecting these waves. So we are selecting them according to 2 criteria. The first one is about their velocity, so we need to have their phase speed that is close to this U700 hectopascal. And the second one is what we saw. These waves need to propagate opposite to the wind relative to the cloud motion. So for an example, so that everybody can understand, if we have a background wind that is completely eastward, and we have a cloud motion that is southeast, the relative motion will be northeast, and we will select all the waves that are in this half circle opposite to this vector. So this is what we get. On the left part of my slide, I'm showing a map of where we find these moving mountain waves. And on the left part and on the right part, I'm showing where we have all our observations. So we can see two things here. First, there isn't a specific place for the generation of these waves. We find them randomly along the balloon tracks. And the second thing we can see is that they only represent a very small fraction of our observations. Now, if we want to characterize a little bit these waves, I'm showing here distributions of horizontal wavelength for the two campaigns, C0 that happened in 2019 and C1 that happened in 2021. The gray field distribution corresponds to all our observations. And then I've distinguished what I call the collocated observations. It's when we had information about the convection around, and this only happened half of the time. So we distinguished the two to be sure that our subsampling wasn't introducing some errors in our results. So here, both of the distributions are fitting. And then the last distribution is in sky blue, and it is corresponding to the moving mountain waves. So we can see that these waves are picking more the smaller scales. And it is reassuring because this is fitting the theory regarding these waves, and this wasn't one of our criteria to select them. So it was a positive point. And then if we want to answer to our question, which is how much do these waves contribute to the observed mountain fluxes, we decided to distinguish 3 zones in the tropical band, as they have 3 different convective regimes: the continents in orange, the oceans in blue, and the maritime continent in green. And I'm showing the corresponding distributions of mountain fluxes for all the observations in the field 1, and the moving mountain waves in the darker line. So to be a bit more quantitative, in average, the moving mountain waves have a higher amplitude than the average observations. But as their occurrence is very small, around 5% in the whole tropical band, we can see that their total contribution is just peaking at 7% above the continents. So now we can move on to the third question, which was trying to quantify just with our observations what is these waves' contribution to driving the QBO. We decided to assess that by looking at how much these waves dissipate between the 2 levels of observations. So I'm showing on the left part of the slide zonal mountain flux in terms of phase speed for the 2 campaigns, C0 in blue and C1 in green, for all observations in the upper panel at 20 and 18 kilometers, and just for the moving mountain waves in the lower panel. So the first thing that is interesting to see is how much more dissipation there is during C0 than C1. We can see here more difference. This peak at 18 kilometers is disappearing at 20 during C0. And we can explain that by the balloons flying closer to a transition phase of the QBO during C1, so when the wind shear was weaker. The second thing that we found is that these moving mountain waves dissipate more than the average observations. If we calculate basically the zonal momentum tendency, so what is the difference between the mountain fluxes at 18 and 20 kilometers, And we know that the drive required for the QBO at these very low altitudes is around 0.3 meters per second per day from models. We actually find that the observed waves represent up to 60% of this drive, and the moving mountain waves represent up to 10%. So even if these waves do not occur often and only represent a small fraction of the observed mountain fluxes, they seem to have an impact on the QBO drive at these lower levels. So, as a summary, I've presented you observations of tropical convective gravity waves and the relationship to convection at different scales. And then I focused on this specific component, these moving mountain waves, and we looked at what is the contribution to the QBO. If you have to remember 4 takeout messages from this presentation, the first one is that I showed that superpressure balloons gave intrinsic observations of the whole spectrum of gravity waves, so they are a very useful tool for atmospheric observations. The second one is that we found that the gravity wave mountain fluxes are dependent on the distance from convection, and we found some sort of background value when we are far from convection. And then we found that the overall waves that we observed were responsible for up to 60% of the QBO drive. And then regarding these moving mountain waves, they didn't appear often, but they seem to contribute up to 10% of this QBO drive. And then as an opening, I'm showing here 2 figures, 2 composites from Bromberger et al. That is in preparation, that shows zonal mean, zonal wind for the 2 transitions of the QBO, east to west, west to east. One run without the moving mountain waves and one with. And we can see clearly that when we add the moving mountain waves, we have a higher amplitude at lower levels. So this is encouraging. And on that positive note, I thank you for your attention.
Thank you. Lots of time for questions?
Hi, I have a quick comment. What you call a moving mountain waves, that was actually an interesting subject of investigation about 40 years ago by people at the NCAR, Terry Clark. Are you aware of that work? That's
Yes.
basically the same. Of course, the difference was that they were arguing about that those waves interact with convection and modulate convection. Here, situation is a little bit different. Convection is kind of independent of those waves. But I'm glad that you are aware of this work, because sometimes the history goes kind of around and people don't remember the old work.
We used that Clark paper
Okay,
a lot for the
very good.
this.
Thank you very much.
Yeah.
There's an onboard radar, a LiDAR, and can you then, looking down, tell whether there's convection underneath it and whether the convection is actually extending up to the balloon height?
So yes, we can see clearly the convection below the balloon level. When the balloons were flying above convective systems, I think it was during the night, they were actually depressurizing. In the study case that I've showed, the balloon actually depressurized for a little bit. So we don't have an extensive data set of when we were flying above these bigger convective systems, but definitely we can see the depth of the convection below the balloons thanks to the LiDAR.
Just a curiosity question. I saw in your maps of the balloons that on the second year they didn't travel all around the world, but in the first year they did.
Yeah.
Do you know why?
There were 2 things. The second campaign had more issues with the balloons envelopes. Some didn't fly as long as during the first campaign. But also we were closer to a transition phase of the QBO, and the winds actually changed direction. So
That was my guess.
yeah.
Question?
I'm just a little curious about how these superpressure balloons work. So the balloon itself is not elastic, it just stays it's the same size, and so it follows a constant density surface. Is that how it works?
Constant, volume. Yeah.
Yeah, okay. Yeah.
And the sunlight doesn't affect it?
Yes.
Heat or cool or
Exactly. That's why we used, for example, I didn't show it here, but for the temperature, for example, we're using the vertical motion of the balloon in order to get the temperature, because the temperature sensors were impacted by this, like some heating plus, yeah. And yes, you can see definitely a cycle in the observations from this heating from the sun. Yeah.
Hi. So when you were filtering your moving mountain waves, you chose only clouds or only points where you had convection within 300 kilometers. Did you change that radius, and did that change the answers at all? How did you come up with that 300 kilometers?
So that came from this figure here. Basically, we found in this paper that the mountain fluxes seem to be dependent from the convection around in a radius of 300 kilometers. And then we have more of a constant value. So we decided to go for that radius, and we changed it, I think, to 500, and it didn't change the results.
Well, it's for the online folks. I think this is working, right? For the online people? Yeah.
So just a comment to that figure, which is great. I think it's a unique data set showing that the gravity wave activity is not going to zero as you go away from deep convection. It's actually going to a background level, and that's what we have learned from aircraft measurements, that you find wave activity far away from wave sources. That's important for microphysics, wouldn't that be? Can you comment on that?
Well, what do you mean it's important for? Yeah, it is important for microphysics. Like that you can have some sort of spectrum of gravity waves even if you're far from convection, and these gravity waves that have high cooling rates will be very important to represent the microphysics in the clouds. Yeah.
Any other questions?
Last part was most interesting for me, that estimate gravity wave effect to QBO. And, well, I guess I got question and concern. I guess concern is it looks a bit too low to estimate influence on QBO with 18 and 20 kilometer height.
Sorry, it was the drive of the QBO just in these lower levels. To know the contribution of these waves to the overall, to the QBO drive, I did that in my 2021 paper. We did another method. We just, I have a slide about it, but it has math. Anyway, we found that it's up to 50% for the whole QBO drive. But this wasn't what I was showing here. It was just for these lower levels.
Yeah, well, I guess my real question is, can you say more positive way how these waves actually influencing QBO evolution.
So you mean how they will interact?
Well, so a way to look at this, my concern is 20 kilometers is probably too low to see it. This symmetry of eastward and westward momentum flux may change with QBO phase. Can you see that with your data?
Oh, okay.
Oh, sounds good
I
question.
see what you mean. So basically, do we see more westward fluxes during a certain phase of the QBO? And no. Yeah, go for it.
Unfortunately, we cannot see that because so far the balloons have only flown in one QBO phase at that altitude region. So yeah, but these balloons are only up in the air for up to 3 months, so they are not in the air for 2 years. So in the next campaign, we are hoping to catch the other QBO phase, and then we can make a statement about your question.
Can I ask maybe a stupid question? If those waves contribute only 50 or 60%, what is the rest? What the rest comes from? Okay, so you don't have done that. There you go. Okay, that's the answer. Thank you.
The online people might not know what's going on right now, but yeah, I can't run that fast.
They should be here.
Oh, yeah, Dan.
So this is probably going to be extremely show my ignorance quite a bit here, but I would like to maybe if you could explain briefly how the gravity waves actually contribute to the QBO, like because unless I'm misunderstanding something, I mean these gravity waves are kind of just going everywhere in every which direction, right, coming from the convection. So wouldn't you expect their contribution to the momentum to be kind of cancel out? How is it that you get an overall westward or eastward contribution, depending on the phase, I guess, for this really large-scale, long-duration oscillation? How does that work?
There is a very nice drawing about this that I do not have in my presentation, but it shows basically some sort of wind profile that is positive, negative, that corresponds to a wind profile that you would have in the stratosphere. And then you have two waves, one with a positive or negative phase speed. And then basically the waves will give momentum to this background wind when they reach a certain critical level. So these waves that propagate up will accelerate this wind. And so you will have this profile that starts like that this critical level is a little bit below the maximum in amplitude of this profile. And so you will have this maximum that will be accelerated and go like lower, 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 as with gravity waves interacting with it. And then you will have that's how it goes.
Okay, thanks.
Okay, let's maybe take one more question or a comment. I'm not sure which it's going to be.
A question.
Okay.
Are you going to do more analysis on how tropical waves influence the formation of cirrus clouds in the future? What are your next plans?
Yes. So after that, I looked at the influence of gravity waves on cirrus clouds during my PhD. We found that we have results that are showing that gravity waves are really important in terms of ice crystals densities. And we want to add the planetary scale waves in order to have a better structure, a more realistic structure of our clouds vertically, in their vertical extension. So I want to add the two.
Okay, let's thank the speaker once more.